All right, so our next piece of the puzzle as we start to look at our thermodynamics is our term called entropy. And entropy is a little tricky in that we're going to measure and say something is more entropic or has a higher entropy as it gets messier, which is a weird way to think about it when we stop and kind of describe our chemicals and our particles and how they are interacting with one another. And so I had this thought. This was a couple of years back. This was right after Thane was born, actually. And our house actually gave us a really good example of kind of the nature of entropy. And it's this idea that as a system, as chemicals, as nature, things always want to move to a greater degree of disorder. And so this was a picture of our kind of our living space, our living room here at home. And so this was, I actually took this night before after the boys were in bed. And so we got everything kind of tidied as best you can for small children. A couple things to note, over here we've got kind of our Thomas toys. We've got, here's our puzzle pieces, yes. We got some books for the boys down here, some stuffed animals, more books over here. And I had to put some work in. I had to put some energy in to get those particles and all the toys and stuff back where they're supposed to be. And then Hugo woke up. And so this next picture was at 9 o'clock the next day. So you'll notice a lot of puzzles had been pulled out. Puzzles had been starting to get tossed. We can see some of the books coming down and out. And so this was 9 o'clock. And then by nap time, so 1 o'clock, the room looked like this. And so all the blocks had been dumped and even more puzzles had come out. And as the day progressed, it naturally became less disordered, or you'd say it has become more and more, or greater and greater entropy or disorder of the system. It's weird to think about it like that we say it's got a bigger volume, the messier it becomes, or the more disorderly it becomes. And that dis kind of makes it hard to think about here. But we give this a name. We call this our entropy. It gets the symbol S. We got a lot of E's, E for energy, right? So we had to come up with something different for entropy. And so we give it the symbol S. And all our entropy is measuring is the disorder of the system. And one of the ways we can start to decide whether something is spontaneous is whether or not it gets messier. We actually can use this entropy idea to help us decide whether or not something is spontaneous. A spontaneous reaction will only occur if it gets us closer to equilibrium. It will never happen if it is further from equilibrium. We already know that from our previous unit. It also turns out it's going to be more entropically favored or more spontaneous if it has greater disorder, if it has more entropy after the reaction has occurred. So some examples. So for example, dissolving salt. That's a thing that happens all on its own. Right? A lot of our salts put into water, they split apart. And this is because it gains more entropy. It has become more disorderly. The particles have all split apart and now they're mixed in more. And oftentimes this is even endothermic, which is weird. Okay, so it actually absorbs heat on its own from the water to then split apart. Well, if it had to take energy in, why did it still happen? Well, it's because it got to split apart into more disorder. Gases, they diffuse. We know this happens all by itself, and that's because they're becoming messier and messier, right? Higher entropy. Certain phase changes. Ice will melt spontaneously above 0 degrees. Water evaporates, even though the enthalpy of vaporization is endothermic. Got to gain energy to go from a liquid to a gas. But the reason we do it is because we get more disorder after we've changed into a gas. And some chemical reactions, for example, sodium reacts very vigorously when you put it into water. Iron rusts. These are all spontaneous reactions, spontaneous changes, things that happen all on their own because they get to be more messy or higher entropy. And so we need to spend some time looking at this. I want to give a little background for this. Don't worry so much about this next piece when we start to talk about, sorry, I'm gonna slide ahead. When we start to talk about kind of the math piece, we're gonna simplify it because it's a state function, which is great. But all it is this letter S. It is the state of order. So if we're thinking about like our phase changes, for a solid, liquid, or gas, we're saying that it has gained entropy as it's gotten closer and closer to that gaseous state. So entropy is a change in the order or a change in the number of ways to arrange the particles. And it is a key factor in determining the direction of a spontaneous reaction. We're only ever going to go towards greater entropy, greater disorder. That is the natural state of the world. So solid to liquid to gas, that entropy is increasing. We're saying that the particles are now arranging themselves in more and more different ways, and so our entropy has increased. It's become less orderly or greater entropy. It's a weird to think about it like that. It's less orderly, so it has a greater entropy. If you're going from a crystalline solid to in a liquid, so you're dissolving a salt, to all of a sudden all the ions are floating around and all the particles, that has also gained entropy. It has lost order. It's more disorderly, if you will. If you put two solid crystals together, forms a gas and some ions in solution, would also be entropy driven. Even though your products might have more energy than your reactants, it might be endothermic, which doesn't make sense. Why would it do that then if it has to take energy in to go? Well, it might be that it just makes enough disorder that it happens spontaneously. It goes all on its own. A couple more examples here. So methane, little hydrocarbon, right? If we were to compare that to, say, ethanol, which is the one down here, right? We say that the larger the particle becomes, the more ways you can rotate it, that actually has more entropy. So the bigger the molecule, the more entropy it has. If you're putting pure solid in a liquid, you got more entropy or more disorder, less order, right? Ethanol and water, that's a aqueous, right? You mix two liquids together, and all of a sudden you got this solution of ethanol and water that has gained disorder. It is less orderly, a higher entropy. As your molecules start becoming more complex, here you can only stretch along your horizontal axis, right? But all of a sudden you put a central atom, now you can stretch in two directions and you can vibrate side to side. As your particles get bigger, larger molar mass, more electron clouds, there's more ways to arrange them. We say that the entropy will increase. Just thinking about how, when we say entropy, what is it that we mean? Well, we mean more disorder, more ways to mix it up. The greater the entropy, the more the mixing, the more the disorder. Cool. A guy by the name of Ludwig Boltzmann actually did some math here. When we start to think about kind of how we can start to describe entropy and actually kind of quantify it, calculate it, right? Because, you know, us chemists, we always want to kind of put some math in there, right? So S equals K ln W. It's kind of the math formula here, where K is kind of our Boltzmann's constant mathematical value. S is the entropy, the actual disorder of the system. Ln, natural log, right? And W is the microstates, or the ways of arranging all the particles. And that's where it gets really kind of funky quick. So if we just had one particle, and we had it in kind of a sealed chamber with an additional chamber beside it, right? So when you open up that kind of valve, it can either be in the first chamber or the second chamber, right? So we'd say the number of microstates for this system is 2 to the first. It's either in one or the other. There's 2 microstates, if you will. If you had 2 particles in there, well, they could both be in one. They could both be in the other. You could have 1 in each, or you could flip-flop them, 1 in each. So it's actually 2 squared. There's 4 different microstates where you can start to put them. If you've got 3 particles in there in a 2-chambered system, well, it's 2 to the third, which ends up giving us 8 different arrangements. But we usually work with moles, which would be 2 to the Avogadro's number. If you plug that into your calculator real quick, what do you get? Yeah, so this gets a little funky in terms of the math here, but just wanted to show you how we can actually math it. We can actually calculate the entropy of a system. The good news is this is already done for us when we start to think about our particles. Takeaway here, don't worry about the math so much. A system with many ways to arrange its components. The larger the W, the more disorder, the higher the entropy. That's the takeaway here. The more ways to arrange it, the more disorder, higher the entropy. System with fewer ways to arrange it, smaller microstates, has less disorder. It would have a lower entropy. And we know, just based on our world experiences, we always are moving towards more entropy. The more mixed up we can be, the more we naturally want that to happen. If you think about your backpack, or maybe the back seat of your car where you throw all your wrappers, or maybe your bedroom at home where you've got stacks of books and stacks of papers and stacks of dirty laundry, we naturally go to disorder unless we put some energy in to undo that natural occurrence. Cool. More entropy, just general stuff you should know about it. Units are joules per Kelvin. This becomes important when we start to math with it, joules per Kelvin. Like our internal energy, like enthalpy, it is a state function. It's not path dependent. Therefore, we could do all the microstate business, blah, but usually for chemical reaction, we can just subtract them. If we take our final entropy minus our initial entropy, we could get just the entropy change of a reaction based upon what we already know to be our entropy of our reactants and our products, which is super nice. It's just kind of final minus initial, like most of our delta values. Cool, just a little bit of thought process to be thinking about. Temperature changes. If you are heating something up, the entropy changes, right? It is more higher entropy, the hotter it gets, because the particles are moving more, they interact and mix more. So the higher the temp, higher our entropy. What happens to entropy in our physical states and our phase changes as you go from solid to liquid, liquid to gas? As you become less orderly, your entropy increases. Entropy increases as you go to a less orderly phase. If you're dissolving a solid or a liquid dissolution, entropy is going to go up. Entropy is going to go up. Cool. Dissolving a gas. Ooh, dissolving a gas. Crazy, 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 crazy. Liquid phase. This actually will decrease the entropy, because we're taking these lots of gas particles and actually mixing them in. We actually see our more orderly system. As a result, our entropy decreases. Atomic size or molecular complexity, as your molecules get bigger, your atoms get bigger, entropy also increases. Increases in mass directly to your entropy. They are directly related. Cool, yeah, good. We're going to be spending some more time looking about entropy and talking about how we start to calculate and kind of look at some of these values, but really just want to give you an idea of entropy and how we start to kind of think about order of the system. What's that going to do for our chemicals and our chemical changes?